We will continue with our discussion on phase equilibrium. Today, I will commence my lecture on two component systems. Before doing so, let me just recall what we did in our earlier lectures. We started with defining the terms that we come across in this topic. We did the derivation of phase rule, then application to water system in details, so that you get a grip on how to use phase rule equation. And we also discussed two similar, at the same time slightly different systems from that of water system. They are carbon dioxide system and sulfur system. With this background, we can definitely move on and apply the phase rule equation to two component systems. My lecture goes like this today. I will introduce you to the two component system, the classification, in which we will deal with solid liquid systems, and within that how these solid liquid systems can be classified, and concentrate on simple eutectic systems. These systems are important because they deal with crystallization problems, distillation, alloy formation, extraction. We can apply phase rule equation to two component systems and see what we get. This is the equation. F is equal to C minus P plus 2. For a two component system, C is of course 2. We want to find out the minimum number of variables required to define the state of a phase. For that, we have to put P is equal to 1, then F works out to be 3. That means we require 3 variables in order to define the state of a phase. What is the result? We have 2 of the variables which we generally use, pressure and temperature. The concentration variable has to be used, concentration of one of the components, so that we have 3 variables with us. How to present the results in a diagram so that we can interpret? We need 3 coordinate axes perpendicular to each other. What is the result of it? We get a solid figure. We know that it is difficult to present this figure, to construct and then use it. On the computers nowadays there is a possibility, but on a sheet of paper or the board, blackboard, it is very difficult to draw and use it. What is the alternative? We can do a projection of such a diagram on a plane, or take a planar cross section for a constant value of one of the variables. We do that so that we can construct a PC diagram at constant temperature or a TC diagram at constant pressure. Is it possible to simplify the study further? We can make an attempt. Consider various equilibria separately, because when you have solid, liquid and the gas, there are various combinations of equilibria possible. We have solid liquid, solid gas, liquid liquid equilibria. So, when you want to have a complete picture of the system, you combine the phase diagrams of all of them. Otherwise, concentrate on that part which interests you and which is your requirement. Let me then start with one of them, solid liquid equilibrium. Very important, as I told you, in dealing with crystallization and purification problems. In solid liquid systems, gas phase is absent, and we know that gas is very sensitive to changes in pressure and temperature. If gas phase is absent, the system is not affected much by changes in pressure. and therefore, we generally study these systems at atmospheric pressure. Let us start with solid liquid equilibrium. In these systems, the gas phase is absent, and hence these systems are called condensed systems. In these systems, since gas is absent, generally we study the phase diagram at constant pressure, and phase rule takes the form F is equal to C minus P plus 1. Of course, it implies that the pressure is kept constant. This form of phase rule is called the condensed phase rule equation. For a two component system, F is equal to 2 minus P plus 1, that is F is equal to 3 minus P. So, simplified form, we have to simply put the value of P to get the number of degrees of freedom applicable to the given system. So, solid liquid equilibria are generally represented as temperature composition diagrams, the so called TC diagrams. In these diagrams, if you have to express concentration, we can use any scheme of presentation of concentration. But then if you have to deal with systems in which the composition varies from 100% of A to 100% of B, the components are A and B in the scheme, then it is better to use either weight percent or mole percent. We start with systems in which there is no miscibility in the solid state, otherwise further complications are added. We will tackle such systems at a later stage. These systems are classified as simple eutectic systems, systems showing compound formation. If there is affinity between the two components, there is a possibility of compound formation, and the compounds may be stable or may not be stable. We deal with systems in which the compounds show congruent melting points, and then look at what happens if the compound is not stable, that is, the compounds exhibiting incongruent melting points. So, let us now take up very important systems that are simple eutectic systems. To form an eutectic system, the two components are completely immiscible in a liquid state, they are immiscible in the solid state, and if we cool the melt, only pure component A or pure component B crystallizes out. Let me start with simple eutectic system. This is the phase diagram of a simple eutectic system. Now that you are experienced in looking at the phase diagrams, it will be possible for you to understand certain things. Now, we said that this is a condensed system and we are keeping pressure constant, it is mentioned here. We have talked about using percent composition, either weight percent or mole percent, we have mentioned it here, and this axis gives us the temperature. When you have 100% A, that means we have pure component, and 100% B here, it is pure component, and you have various mixtures of A and B covering the entire range 100% A to 100% B. Now, as you heat it, the stage comes at which the solid A melts, that is the melting point of solid A. Similarly, we have melting point of solid B. Now, above the curve shown here, DEF, only liquid state is present or the liquid phase is present in the form of a melt or a solution. Therefore, the curve DEF is called the liquidus. What do you mean by liquidus? Curve above which only liquid phase exists. If there is a liquidus, there has to be a solidus also. Below D, A is in the solid form, and along the line D, G, E, H, F, we have only solid phases. Therefore, this is called the solidus. So, we have melt on the higher top part of the diagram and solid at the bottom part. In between we have two regions in which the solid is in equilibrium with the melt. On one side we have solid A in equilibrium with the melt, on the other side we have solid B in equilibrium with the melt. Yes, there is one characteristic point here when the two curves meet, which we call the eutectic point. Why do we call it eutectic point? We will see at a later stage. This is the place where we have solid A, solid B and the melt in equilibrium, which is shown here. When there are three phases, the system becomes invariant, because when there was one phase, it was a case of bivariant system, and when two phases are here, then it is called the univariant system, and here it is invariant system. So, at point marked E here, number of degrees of freedom is 0, you have an invariant system on hand. That means the eutectic point represents an invariant point. Certain elaborations have to be made here. The vertical line corresponding to constant composition here is called the isopleth, and the horizontal line that we draw at constant temperature is the isotherm. Now, if you remember, if this is the melting point of pure B, addition of an impurity into it is going to decrease its melting point. You can consider component A present in B as an impurity, because of there is a decrease in its melting point. As you go on increasing the amount of A in B, the melting point successively decreases, and you can clearly see that. Same thing will happen to solid A. When B is added more and more, its melting point goes on decreasing, and here the two curves meet. An interesting study will be what changes take place in the system along the isopleth. For understanding that, we must remember that there are horizontal lines which we call the tie line. What is a tie line? The two ends of the tie line are useful to us. They give us the composition of the melt in equilibrium with the solid. Here you have a tie line, solid A, one end corresponds to which solid, and the other end, which is on the curve DE, gives us the composition of the melt that is in equilibrium with the solid. So, our overall composition of the system that we have taken is this. When you take it to this temperature, it splits into two, solid A and the melt. Let us find out the changes that are going to take place as we move along the isopleth. We start with a mixture of definite composition and heat it and take it to point X in the diagram. That is X, it is in the molten state. We have 2 degrees of freedom. It is a bivariant system, and if we start cooling it, system does not resist. The temperature decreases and we reach the point Y on the curve DE, at which solidification commences and some solid A crystallizes out. As the A is removed from the melt, the composition of the melt starts moving towards the right along this line. That means the melt becomes poorer in A as A is removed as solid, and the melt becomes, on the contrary, richer in B. So, we were having 2 degrees of freedom till Y. At Y, when there are 2 phases, we lose 1 degree of freedom, F becomes equal to 1, and from this onwards cooling is allowed, because we have 1 degree of freedom still left with us. And as cooling takes place along the line Y Z, more and more of solid A comes out. In the process, the melt becomes poorer in A and its composition starts drifting along the line. Ultimately, when you reach the point Z on the horizontal line here given by GH, the composition of the melt will reach the point E. So, in this region, the system is present in two phases. One, the solid which starts crystallizing out as you cool it from here to here, and the melt whose composition starts drifting here. So, along line GH, the curve you have FE intersects it. That means, you have similar situation here. If you cool a melt of this composition, which is B rich melt, which is having 1 degree of freedom, the univariant system, that means we have solid B and the melt that are in equilibrium. But the melt composition in either case has finally reached point E. At point E, there are 3 phases in equilibrium: solid A, solid B and the melt. Number of degrees of freedom becomes 0. The cooling stops. The radiation loss is there, but the system resists because temperature cannot change. This composition corresponding to point E is called the eutectic composition, and the temperature corresponding to this is called the eutectic temperature. Is it possible to separate pure component from the mixture? Let us try to answer this question. You look at the figure. From Y to Z, as you show Y to Z, the solid A was separating and it had sufficient time to grow. The amount of A separated out from Y to Z is pure solid A. Similarly, from this point to this point on this side, on the right side, you have solid B separating out. But if you stop just above point Z and separate out whatever solid that has come out, it will be pure solid A. Similarly, on this side, it is possible for you to separate solid B. But if the temperature comes down and touches the horizontal line, which we called the eutectic temperature, you will have solid A and solid B together. That means the contamination has taken place. So, if you are interested in separating pure solid A or pure solid B, you have to stop cooling just above the eutectic temperature. But another point you can see here, if the overall composition is to the left of C, it is possible to get solid A. If you are to the right of it, you can get only solid B. You will not be able to separate both solid A and solid B in the pure state. It will be very interesting to study the behavior of a system in which the composition corresponds to point C here. C is the eutectic composition. If you heat it and take it to the molten state and then cool it, as you reach point E, the system becomes a 3-phase system, because the two lines intersect. Solid A and solid B crystallize out. 3-phase system means number of degrees of freedom 0, system becomes invariant, cooling is resisted till one of the phases disappear. In this case, the molten phase disappears and then you go below the solid S curve. Some elaboration of eutectic mixture is needed. Eutectic point is characterized by a unique temperature and composition, reason being number of degrees of freedom 0. Why it is called eutectic point? Eutectic means easily melting. The mixture has a sharp melting point, and it was thought that it is not a mixture, it is a compound that is formed. Now, we have to rule out that possibility. How do you rule out? If you watch it in a microscope, you can see distinct phases. The two components are not present in the molecular ratio. It happens in the case of compound, for example, H2O, they are in 2:1 ratio. But here the components are not present in molecular ratio. Not only that, if you change the pressure, composition of the eutectic solid changes. If one of the constituents A or B is added, to it and look at the melting point, the melting point must show a fall if it is a pure compound. But in this particular case, the diagram tells us that addition of either A or B to the eutectic composition, that means if you are to the left or right to the point E, there is an increase in melting point. The physical properties, if you look at, they are almost the average values of the properties of the individual components. The properties such as heat of solution, density are equal to the mean values of the two components. Here we have a system which more or less gives us an eutectic phase diagram. It is a bismuth-cadmium system. There is no miscibility between bismuth and cadmium in the solid state, but in the molten state they are completely miscible, and it is a single phase system. That is why I have written an unsaturated melt, and on this side you have solid bismuth crystallizing out from the melt. On this side you are having solid cadmium separating out from the melt as the systems are cooled, and you can get an eutectic composition where bismuth and cadmium are in the right proportion corresponding to eutectic. So, this much information regarding eutectic system will help you to understand future systems that we are going to take up. Let me summarize what we have seen today. We started with two component systems. I introduced you to the two component systems, taking off from what you learned from one component system, the classification of two component systems, out of which we chose solid liquid system for our studies. Further classification is there in it, and we went to simple eutectic systems. In my next lecture, we will take up systems under this subhead where the components A and B have some affinity and form a compound. The systems are of two types in that: systems in which the compound shows congruent melting point, and the systems in which the compound shows what is called incongruent